not cover. It's part of the basic science courses. So we're going to talk about cell structures, the chemistry that takes place in the cell, and many other foundation knowledge that you would need for clinical stuff with people when they're coming. So at least you have idea what's going on, at least at the molecular level, cellular level, and so forth. Now, if changes occur that may affect the normal cellular processes, so disease takes place. And that's basically what we are here to give you information about. So you will not see all the biochemistry, for those who already got a biochemistry courses, you will not have everything that you already seen before in this part of the course, but some of the biochemistry lectures are distributed to the system courses that you will see. So if something is missing here, you will see it in the system courses. So the first thing I put here is the life definition as a biochemist. Some can argue that. But for us as a biochemist, as you heard, life is chemistry, right? So basically, as far as we're concerned, as biochemistry, it is a concerted manifestation of a chemical reaction taking place in living things. Living things as us. So we're going to focus ourselves in a human being. Since we're going to be a healthcare provider, so chemical reaction taking place in a human being. So life is a chemistry. As a biochemist, our job is to study those chemical reactions, okay? How they proceed, the normal procedures, and when they go bad, the disease process takes place. And sometimes we'll give you some clinical correlate and how to fix them and so forth. But clinicians and pharmacologists also come and give you some more information on this. But our job is to give you the foundation. So chemical reactions being said, so in our body there are thousands of chemical reactions taking place. And they're taking place in the aqueous environment, which make water a very, very important molecule. So if you take our body, an adult person, you have like a 60% of your body weight, it's about 60% of your body weight is composed of water, okay? For younger folks, like babies, they can go even to 75%. So which make water the most abundant molecule in our body. And that's for a reason. It's a very, very important molecule. It's a polar molecule, so things can be dissolved in it. So it is a good solvent, but in the same time, it can transport chemicals to site where chemical reactions take place, okay? So what is important that way? But sometimes, water even dictates the direction of chemical reactions, okay? So part of like in the hydrophobic forces, water play a big role. Even though hydrophobic molecules are not soluble, but water will push them to stay together, okay? So that's the role of water in those entities. So that being said, chemical reaction taking place, so water has all of these properties. And these properties are based on some specific structure of the water that, I'm presenting here. So if you look at a water molecule, okay, I'm sure all of you know H2O since the 6th grade, right? So water is composed of oxygen, and oxygen is highly electronegative. So you pull all the electrons to itself. Electron being negative. So this edge of the water, as you see here, is relatively negative. And the other pole is relatively positive, because much more electronic than the proton. So one edge of the water is negative, and the other edge is relatively positive. So that makes a dipole, like a battery, okay? You have a negative end, you have a positive end. So basically, that is the structure, these characteristics that really define the property of the water. That's why water has all these other properties, as you see. So a good solvent. So now, the water molecules, if you're in the water liquids, or even in the solid form, you have what's called hydrogen binding that form between water molecules. You have a hydrogen relatively negative, and the hydrogen relatively positive, and oxygen relatively negative. Positive attract negative. So this is called the hydrogen binding between water molecules. So within the water molecule, you have a lot of hydrogen bonding, okay? And these hydrogen bonding are relatively strong. I'm sure all of you seen a boat on top of the water floating around. Don't go down. because those combined forces of the hydrogen bonding is so strong it can even support a boat. Okay, so that's why hydrogen bonding in the water are relatively strong. They can support weight. Now, again, as a dipole, positive and negative end, if you take a salt, you put in the water, I'm sure all of you have done that before, and you mix it out, by the time you know the salt disappears, right? So the salt has dissolved in the water. What happened, the sodium chloride will break into two, sodium and chloride being negative and the sodium being positive. So if you look at the water molecule, nice to everybody, the chlorine, relatively negative, will interact with the positive end of the water, the hydrogens. So you have those ionic interactions. Now, the other hand of the water, which is negative, the oxygen side, will have interaction with the sodium, and sodium is positive. So positive attracted by negative, so everybody is happy. Does that make sense? All right. So the next things, you know, in our body, we have thousands of proteins floating in the blood, in the cells. All those proteins are also soluble in the water for the same specific reason. On top of the protein, you're going to see that soon. Dr. Lucia is going to come talk about amino acids and peptides and so forth. You're going to talk about those amino acids. Proteins being composed of amino acids, so they have a composed of amino acids. So those amino acids, some of them are polar, okay, but some are hydrophobic. But the polar molecule, amino acids are on the surface of the protein, and the hydrophobic ones are inside. They're hidden away from the water, but the polar molecules, amino acids on the surface, start doing the very same thing that I just described with the salt. The positive side chain amino acid will interact with the negative, as you see here. If you have an amino acid here that is positive, it will interact with the negative end of the water, and vice versa, the negative amino acid will interact. Even just those that are now charged, they can still make a hydrogen bonding with the, if they're polar, they can make a hydrogen bonding with the water, okay? So water makes everybody happy, except the hydrophobic one, they try to hide away from water. So even that, it is important, because the hydrophobic amino acids are inside. They stay there because they're afraid of water, they don't want to come out of the water, and they stay inside, okay? Now, the hydrophobic effect. I said that a non-polar molecule, make a correction on your slide. This is a non-polar. I know it was there polar, but it's non-polar, okay? Make sure you make that correction. So non-polar molecules such as oil, when you take an oil, you pour in the water, what happened? The oil molecules start to stay together, right? They're heating away from the water. So they're trying to come together and stay away from the water. Basically, water molecules come and cover them, form a shields around them, and keep them together so they don't come out, okay? They don't want to be in contact with water. So that interaction is non-favorable because they don't want to interact with the water, okay? But if you put two non-polar molecules next to each other, you can correct this one, so non-polar, non-polar, non-polar here, not polar on your slide, okay? So when you put two hydrophobic molecule or oil, for instance, next to each other, this interaction, the initial interaction is now favorable, but once they manage to come next to each other, they will chase away all the water molecules and come together and form just a single one because they like each other. They're all hydrophobic. They come away, and the water molecules form a shade around them. That interaction is favorable, okay? Hydrophobic molecule trying to come together. And that is very, very important. Because the reason proteins, when the proteins are synthesized, as I'm sure most of you have heard about translation, proteins are synthesized as a peptide. But they have to fold to the native conformation. And one of the forces that drive that reaction is a hydrophobic interaction. The hydrophobic amino acids are so scared of the water, they come and hide inside the protein and stay there. And that is important. If without that, they will come out and the protein will denature. So because of that hydrophobic forces, non-polar amino acid, the hydrophobic one, will go inside and stay there, okay? Outside, the hydrophilic amino acids are there, they interact with the water. Does that make sense? So that's why I keep protein in their native conformation folded forms, okay? As you see here, you have your peptide, it's folded. Even here, it's much more clear. So this is your peptide. The hydrophobic amino acids are hidden inside, and hydrophilic ones are outside and interact with the water, okay? That's why it makes the proteins stay in their native conformation. It's very, very important. Even though hydrophobic molecules do not like water, but the fact that they stay inside, that's what you want. The proteins stay together, okay? I'm sure you see when you see milk, it's nice and homogeneous, but once it denatures, the casein denature in the milk, you start seeing these clumps, right? Because the hydrophobic proteins came out, but now they cannot form a native conformation. Now they come together and form clumps. That's why when water is denatured, the milk is denatured, you will see those clumps as the casein clumps in the milk. Does that make sense? All right, good. Now, that will lead us to acid base. So a third property of water can dissociate. So water can behave like an acid, okay? Now, a strong acid, relatively weak acid. So when you have water molecules in the solution, they would basically dissociate it to H plus and OH minus, okay? But very small amount of the water dissociate that way, okay? So the Ka is characterized, any equilibrium, you have what's called equilibrium constant, Ka. The Ka is characterized by the amount of protons, hydroxy ion, as far as water is concerned, that is dissociated. The product of that ion concentration over the remaining acid in this case. In this case, water will be acid, okay, when it dissociates, okay? Now, that ion product, you can calculate that by taking the concentration of proton that is the water that is remaining, and then times the K equilibrium, so that will be your ion product. The product of the H plus times the OH. And these two concentrations are the same, right? Because from one water molecule, it splits to one hydrogen and one hydroxy ion, okay? So the product is called the ion product. So the two concentrations are the same, and that's called K water. This is not that critical to you, okay? Just to give me a baseline for us to understand the acid-base chemistry. So you don't have to, if you don't understand it, don't worry too much about it. It's a very simple concept, but just to give you an idea. Now, the products, these two, is 1 times 10 to the minus 14 molar squared ion product, because the concentration of water, the hydrogen in the pure water and hydroxy, each one of them has 1 times 10 to the minus 7. So the product of the two, so 10 times the minus 4 molar squared, okay? So that's your ion product. Now, that's what it said here. So as I said, pure water, the concentration of proton and the hydroxy ions are equal. So because they're equal, so each one of them will 10 times minus 7 molar, very small amount, as you know, 10 times minus 7. So now, in certain condition, when the proton concentration in the water increases, for whatever reason, you add an acid, the proton concentration increases over the hydroxy ion, so the water is, at that point, is called acidic, okay? Conversely, when the proton concentration is lower than hydroxy ion concentration, so it is called basic, okay? So the proton concentration, the fact that you're dealing with 10 to the minus 7, 10 to the minus 8, very difficult to deal with when you do a calculation. So they came out with a new concept called the pH, and that's what we're going to talk about. So basically, before I show you the calculation, the pH is an estimation of the proton concentration, okay? So pH is an estimation of the proton concentration, because you do not want to deal with the 1 times 10 to the minus 7, 20 times 10 to the minus 5. You want to deal with the one single number. And that's the purpose they came out with this theory of the pH. So by definition, pH is equal to minus 7 of the proton concentration in the solution. So if you take any given solution, the proton concentration, you evaluate that, and minus log of that concentration is your pH, okay? In the case of pure water, the proton concentration is 10 to the minus 7. So when you say pH, it's a minus the log of the proton concentration. In the case of the pure water, the proton concentration is 1 times 10 to the minus 7. And if you take a minus log of that, so that is 7. That is why they call the pH of the pure water is what? 7, which is the neutral pH, all right? Okay. Another concept I want to add it on. So the total of the pH and the pOH, which are another estimation, but the OH concentration now, okay? But the sum of the two, when you calculate the pOH, which is a minus log of the hydroxide ion concentration, and pH minus log of the proton concentration, if you add these two values together, so it is 14. Okay, put that on your slide there, and I'll just add it up. You know, it's extra, because you may see, you know, I get a little worried if some stuff may come on the board exam that I'm not sure, so I want to make sure you have this, okay? So pH plus pOH is a minus 14. So given the pH concentration, you can calculate the pOH by subtracting the pOH. If you want to calculate the pOH, you take 14, you subtract the pH value. If you want to calculate pH, you take 14. If you have the pOH value, you subtract that to 14, and vice versa. Is that clear? Good. So now, it turns out when the proton concentration increases, we are in an acidic condition, and the pH is lower, right? As the proton concentration increases, the pH decreases because it's minus log of the proton concentration. So, and then when the proton concentration decreases, the pH goes up. Okay, that's a concept that keep in mind. Okay, take yourself, put yourself at a pH 7. Okay, so the proton concentration 10 to the minus 7. The pH will be equal to 7. So now, if the proton concentration goes up, so in the acidic condition, so the pH goes down. Okay, so keep that in mind. The pH and the pOH go in the opposite direction. And the proton concentration go in the opposite direction. Proton concentration and pH go in the opposite direction, okay? If proton concentration goes up, pH goes down. When the proton concentration goes down, pH goes up. And this is important. It can help you to put yourself always in, in perspective when you're looking at the pH and the proton concentration, okay? So I put that in there so, to give you an idea. So now, when you calculate it, basically, you have a solution at the pH equal to 4 times 10 to the minus 5 molar. So calculate the pH. So basically what you do is, just like I did with the water, so you take the proton concentration, you apply the minus log, and that will give you a value, in this case, 4.7, 4.4, okay? So if you look at the proton concentration here, compared to the proton concentration in the pure water, high or low? High, right? So, which means the pH is lower than 7, right? Compared to pure water. Good. So now, first case, since you're going to be clinicians, so put it in this perspective, all right? So Diane, a diabetic patient, was brought to hospital unconscious. The blood sample was drawn and sent to the lab for analysis, and the laboratory report indicated the pH of his blood is 7.08, okay? And the range of pH on our blood is between 7.37 and 7.43, okay? So what is the proton concentration in Diane blood compared to the pure water? Oh, compared to the range, all right? Okay. So the proton concentration is high, and that is due because when the diabetes, sometimes with type 1, when uncontrolled diabetes, the person that is not controlled can have ketone bodies generation. And ketone bodies are acids, weak acid, but they're acid. So they produce a lot of proteins in your blood, which can decrease your pH. But the proton concentration goes up and the pH goes up. Is that clear? That is what's happening here. You'll see more of that, but at least give you an idea how your pH can change over time due to a disease. So importance of the pH. When you go to a laboratory, pH is very, very important. In the molecular biology labs, biochemistry labs, even cell biology lab, pH is very, very important. because biological molecules are very, very sensitive to pH, okay? It doesn't mean everything has to be in the pH 7 or the pH of the blood, but the condition of the environment that is necessary. For instance, when the protein is in the blood, it's much more to be on the optimal condition of pH 7.4, right? But if the protein is in your gut, the 7.4 is going to be the optimum pH. Exactly. So pH can change depending on the area where the protein normally function. So when you take them out of that range, so then protein, if a protein work normally, for instance, trypsin in your gut, if you in your stomach, so when you put that trypsin in an environment where the pH is 7.4, it will work, but not as well as it should in the pH 3 or 4. Does that make sense? Even though it's a protein, okay? So now, if you go, you take a urine sample or blood sample, they will check the pH, make sure, because it gives them idea what's going on in the patient's body, okay? So sometimes you have what's called acidosis, which means the person's pH of the blood is lower than the normal 7.37, or it could be higher than 7.43, which means it's alkalose. So basically, the proton concentration is high or low. Alkalose. Okay. And then, so diabetes, as I said, type 1, sometimes the pH changes occur that go down because the proton concentration, you have a lot of acid production going on. Okay. So for instance, if people who is exercising a lot and lactic acid buildup can also change pH in the muscle. That's why you feel pain sometimes when you exercise too much. While after a long period of non-exercise, those lactic acid buildup can cause drop of the pH. Okay, but it doesn't mean pH is always bad when it goes down. Sometimes it has a regulatory role, especially with the hemoglobin, and we're going to talk about that, in a few lectures down. Okay, so pH changes sometimes has some benefit. Okay. Signaling purpose. All right, so that being said, we'll talk about pHs. Now, acid and base, okay? The acid, by definition, is a substance that rises the proton concentration in the solution. Okay, if you have water, you add a little bit of acid, what happened to the pH? Down or up? Down. Proton concentration, down or up? Exactly. So base, on the other hand, it's a substance that decreases the proton concentration in the solution. When you add a base in the solution, it will take the protons away. So the proton concentration in the solution decreases, so the pH goes up. Okay? So that's base. And these are basically the definition of Bronson-Lowry that came out with these ideas of pH definition and so forth. Okay? So when the proton concentration decreases, OH concentration increase, the pH is high. When the proton concentration increase, the pH is low, and that's in the acidic condition. So I gave you here the range, pH from 0 to 14, that's the scale. And if you look at in our body, a different, for instance, a human blood and tears, the pH is slightly on the alkaline side, 7.4. But the milk, for instance, and the saliva is slightly low. Compared to but coffee and so forth, all this stuff, as you can, you're drinking all the time. For instance, coffee and so forth. Yeah, it's relatively acid, okay? So they were trying to decrease the pH in your blood, but your body has a resistance against it, okay? Which is the buffer system, and we're going to talk about the buffer, okay? So now, the ionization. This is a very important concept because it really gives you an idea how amino acids in the future in a protein can behave depending on the changes to pH, okay? For instance, when you take a benzoic acid, okay, this group, the carbonic acid, would be, it's an acid which is going to be nice when the pH is relatively lower compared to something called the pKa, and we're going to talk about the pKa very soon. So it will give out the proton, so you have the proton now given the environment, so you have this, what's called the conjugated base, okay, which is the ionic form of the molecule, which is a negative here. So this is a conjugated base, and this is your proton. You have a dissociation. And this dissociation is characterized by this the dissociation constant called the Ka, In this case, it's 6.3 times to 10 to the minus 15. So that's your dissociation constant. Okay. And the dissociation constant, this is the formula. Same thing as you have with the water. You know, you have the water dissociate the proton and the conjugated base, which is your OH on the water case, and over the remaining acid concentration. Okay. So now that's your Ka, and this is a characteristic of this acid. Okay. Now, if the Ka is higher than 1, okay, so you have what's called a strong acid. A strong acid will dissociate completely, but what a weak acid dissociates partially. So keep that in mind. The Ka is higher than 1, and the Ka in the weak acid is less than 1. So strong acid, the HCl and so forth, sulfuric acid, those are the strong acid that you see in inorganic acid. But these are the ones that is of interest to us, called the organic acid, the weak acid. And our body produces a large amount of this every given time, okay? And you have to get rid of them, at least balance them. So they are called the weak acid, lactic acid, the ketone bodies, which are here, the acetic acid and butyric acid. Those are the ketone bodies. Okay, that Ka value is low. So the Ka, you see the Ks, the acid, the proton, ion proton over the acid remaining concentration. So now there is another thing called the pK, okay? Just like you see with the pH, the pK is a minus log of the Ka value, okay? That's another characteristic that defines basically the Ka. Instead of dealing with the Ka, as you see here, 6.3 times 10 to the minus, which is very hard to deal with, working with when you do a calculation. It's easy to work with something called Ka, which is just a single digit, at least, you know, or maybe 1 or 2 digits, okay? Very simple to deal with. So pK, it's log of the, minus log of the Ka. But basically, it defines how well an acid will give up its proton to the environment, okay? So the pK value, one thing you have to remember, the pH change, the pOH change, the pK doesn't change for the acid. Keep that in mind, okay? So it's like the acid last name, the pK is fixed, so any given acid it has a specific pK, okay? So keep that in mind. So now if you have a carbonic acid, benzoic acid, the pK value 4.2 doesn't change. So which means this guy, when the pH go beyond this guy will behave like acid, he will give up his proton, okay? That's what the pKa means. When you go beyond 4.2, he will give up his proton and become ion, okay? The same thing here, what this means, the pKa value for this amine group, what that means? He will give up his proton when the pH is above 10. Does that make sense? So when the pH above 10, this guy will give up his proton and become NH2, okay? Not NH3 plus, but not NH2, because it gives us his proton. That's what the pK really means as far as we're concerned here. So how about here? No pK because it cannot give up the protons, right? So it doesn't have any pK. Okay, as I said, the pK doesn't change as the pH changes. But the pH, the proton, the acid will give up its proton when pH changes, or accept it when the pH changes. Does that make sense? All right, here, all right, this is an example. So now, if you take this benzoic acid, you put at the pH 7, which one of the following form will be much more prevalent? The top one or the bottom one? This one or this one? Bottom, right? Which means we are above 4.2, we passed the 4.2, so this benzoic acid now will be a good guy. We give up its proton, try to contribute to the resist to the pH changes, okay? Now, how about if you go below 4.2? Which one will be much more prevalent? The top one, right? That's correct. So the top one is the protonated form, and the bottom one is the deprotonated form. Okay, keep that in mind. Because sometimes in some of the exercise we have, you have a protonated versus unprotonated. The concept sometimes be confusing. The protonated means it has a proton attached to it. The deprotonated, it lost its proton, okay? Sometimes protonated, unprotonated, or deprotonated, same thing, okay? deprotonated in this case, so it lost its proton. Okay, as you see here, so pH, the pKa 4.2 is here. So when your pH go beyond the 4.2, you have these forms prevalent. If you below it, this form is much more prevalent. Okay, now metabolic acid. So if you recall, I said in metabolic basis, our body produces a large amount of 13 to 20 mole per day. Imagine you produce that much acid in your body. Okay, and these are leaking to your blood. Now your cell, as I said, proteins are very sensitive to pH changes, right? Biomolecules are sensitive to pH changes. So you get all this occur. The reason is because CO2 is formed. Where does the CO2 come from? You know, when you take in sugars, food stuff you're eating, they go to a process, glycolysis, if it's a carbohydrate, Krebs cycle, where you have a generation, a lot of CO2. So basically, the organic molecule taken in the food stuff, they get digested, they get metabolized for energy purpose. At the end of the day, you generate a lot of CO2, right? And those CO2 can be dissolved in the water, and there is an enzyme called carbonic acid would directly convert them to, it's not in forms of gas, but in a dissolved as what's called carbonic acid, H2CO3, which is basically acid, right? So, and this acid can just break down to proton and bicarbonate. So the proton concentration is increasing because you have produced a lot of CO2. Because any given time you are eating, you're digesting it, you're metabolizing, you generate a lot of CO2. So the CO2 level goes up in your tissues, and then they leak out and convert to carbonic acid, and the acid will give out protons, so the pHs are dropping in your blood or in your cells. You have to get rid of it somehow, right? Because the level goes up, so you have to get rid of them. So you have a bunch of molecules formed out. And lactic acid also formed from pyruvate. You'll see that in the glycolysis. You generate a lot of lactic acid. You also generate a lot of ketone bodies and through the fat breakdown acetyl-CoA forming ketone body. But this is the major source of the acid in our body, okay? But sometimes, one thing I want to bring it to your attention, sometimes, I'm going to say CO concentration, which is basically the indication of carbonic acid. So if you're reading a textbook, you see that CO2 concentration, really, because CO2 is going to convert it directly to carbonic acid. So sometimes people use that one way or the other. So if the CO2 goes up, carbonic acid level goes up, okay? And it produces a bunch of these, and so acids are produced, and they should be cleared up in the body. This is very, very important, okay? All right. So now you're producing a lot of CO2, and they're becoming carbonic acid. The proton concentration is increasing, the pH is dropping, right? And you have to take care of that. So there is a system that we call a buffering system. And we have a nice system about it. I hope you have a nice system in order to take care of those acids that is producing. One example of buffer, you probably heard of buffer, but it is a very simple concept. A buffer is nothing, a mixture of acid and its conjugated base. Okay, you take an acid, in this case, let's put it up, an equal amount of acid and its conjugated base, you mix it, you have a buffer. And this mixture will resist to pH changes. Basically, by doing what? When you add a base, okay, the pH will try to change, right? Because the base, the OH will try to take on the proton, and then the pH goes up. What happened, the acid that is here, this acid, H2SO, will give up its proton, and the hydrogen will enter up with hydroxy, that is, you just added, and to form water, okay? So when that occurs, the proton concentration will not change. Now the proton concentration will not change because this guy gave up his proton to compensate it for the hydroxy you added on. Does that make sense? Now, conversely, when you add acid in the solution, so the proton concentration will try to rise up, right? So what happened, the conjugated base will accept the proton and then become an acid. So the proton concentration in the solution will not change. Okay, or at least it is minimized. Does that make sense? So a buffer is a substance, when you add a base, you absorb the base. If you add an acid, you absorb the proton or the acid. Yeah, same thing. Does that make sense? You add a proton, you absorb it. You add a hydroxide, you absorb it. So it will resist the pH change because by definition, pH changes occur when proton concentration changes. All right. Now this is the same concept. So when you have a solution, in order to identify what, for instance, you want to work on the solution, conduct experiment, and you want to stay in a certain pH, okay? And you want to identify which molecule buffering system you should be using. So basically, the titration will help you to tell what system you should be using. So for instance, you have a pH 0, and you start adding hydroxy to the solution. What happened to the pH? You added hydroxy. The pH will start to rise up, right? Exactly, that's what happened. You see, you add hydroxy, the pH will rise up. But it turns out when you reach a certain point, you keep adding, but the pH is not changing. Because the carbonic acid, here, the acetic acid, start giving up its proton to counter the hydroxy you're adding. But the same process I explained earlier. So it will give up its proton, and that proton will interact with the hydroxy group, so the pH doesn't change. And that occurs at a certain point close to the pKa value of the acetic acid in this case. So you have a resistance, and until you reach a certain point, now you have changes because you got rid of you lost all your acetic acid, so the pH starts changing because there's nothing else to counter the hydroxy ion that you added. So the point exactly here where you have a maximum forces to resist the pH change is called the maximum buffering capacity. At that point, the pH is equal to the pKa value. You see here, the pH at which is equal to pKa value, that's your maximum buffering point. And the pKa value plus 1, pKa value minus 1 is your optimum buffering range. Okay? So the maximum buffering point is the pH is equal to pKa. And the range is plus a pKa plus and minus 1. Okay? That's the buffering range. All right, so Anderson Hasselbalch, you probably heard this before. This is a very good concept. And we're going to talk about the formula, and then we're going to explain, the physiological importance too. Okay, if you look at Anderson Hasselbalch, so basically you have the acid dissociate, and this is the formula. Basically what this formula said, which is the pH, pKa plus and minus the ratio as conjugated base to acid. So basically, this is your conjugated base, and this is the remaining acid, the ratio. So what it's saying, the pH changes doesn't depend on the pKa, because you remember the pKa is fixed, but it depends on the ratio of base, conjugated base over the acid. So if this ratio change, the pH changes, okay? And this is very, very important for this reason. This is the calculations that I put it in there. I don't know if you've been able to do at home, but if you look at it, you have your pKa value that doesn't change. Carbonic, in this case, you have your acetic acid, the pKa is 4.76. If this ratio, you have 90% and the remaining acid, it's 10. Because the sum of the two should be 100%, right? So if you have this ratio, if you have more D protein over acid, and then you take this ratio as 9, log of that will be around 0.954. So now if you add that in this, you have your 5.71, okay? Now, imagine if these two, the ratio was equal to 1. If the ratio of the conjugated base and the acid was equal to 1, what would be the value? Log of 1 is what? So what is the end of the at the end, so the ratio will be 1. So log of 1 is 0. So basically, the pH is equal to pK value. So that's the 50-50 rule, which means that when the proton concentration, the acid to base ratio is equal to 1, the pH is equal to the pH is equal to pK value. So now that will bring us to the most important part of this thing. Okay. Excuse me. So if you have, as I said, the carbonic acid is generated when you have CO2 generation to metabolism, okay? Now, they will dissolve it to carbonic acid, then we dissociate it. We have this bicarbonate to proton, and as I said, the conjugated base to acid ratio. So if in your body, this ratio is a fixed value, okay? But when it changes, so what I said, the changes of this ratio is the one that affect the pH, but not the pK, because the pK value is fixed. So when this ratio changes in your body, then the pH will change. Okay? Does that make sense? Good. So, and that has a very much important physiological function, role. So in case, look at this. As you see, I took it out the pK value, right? So as the bicarbonate constant, which is the conjugated base, goes up, so this one, the ratio will change, okay? When this go up, so the ratio will go up, what happened, the pH goes up, okay? Because the hydroxy ions level, not the hydroxy ion, the conjugated base goes up, so the relative ratio over acid goes up, okay? So the base over acid goes up, so then the pH goes up, okay? So that means that for some reason, if you're losing protons and the bicarbonate level goes up, the ratio of conjugated base of acid goes up. As I was saying earlier, the CO2 really means carbonic acid, okay? So if this ratio goes up, the pH goes up. And what happened when the ratio goes down? Go down, right? All right. So here, this is called metabolic alkalosis. The pH is going up. Yeah, basically, you have much more base in your body than acid, so you have alkalosis, metabolic alkalosis. And you will see this concept much more in physiology and so forth. But you know, I want to introduce for you, at least you have an idea in the biochemistry standpoint in case you see that before you see another thing. So now, when the ratio goes down, the pH goes up because the carbonate level goes down in reference to carbonic acid, so the pH goes down. And that is called metabolic acidosis. Okay. So now, conversely, same thing as the bicarbonate can change, the carbonic acid can change also. When the CO2 level goes up, and the CO2 level goes up, again, the acid is going up, so the pH level goes down, okay? Because you're adding more acid on the environment, so the pH drops. Does that make sense? All right. So same thing when the CO2 level goes down for some reason, okay? So the ratio is then higher. So you take a log of that, then you'll see the pH have changed. And this is respiratory alkalosis because for some reason the person is getting rid of all the CO2 and then the CO2 level goes up. In what condition can you get rid of your CO2? Huh? Yeah, if you're breathing hard. Now the CO2 goes up when you're breathing less, right? When you're breathing less, you're not exhaling the CO2. So the CO2 level will build up in your body. When you're breathing too much for some reason, you have a condition, and the CO2 level goes down, then the pH goes up. Is that clear? Good. All right, so your body has a buffering system. Bicarbonate play a big role in maintaining your blood pH, hemoglobin, and so forth. But respiration play a good role in it. So when the pH starts changing, your respiration can adjust to it. But also your kidney can also play a big role in the pH change. So you see, when the acid, for some reason you have a respiratory mediated acidosis, so your kidney can get rid of the proton this way in forms of ammonia to balance it, okay? So you have your respiration to maintain it, but you also have your kidneys to maintain your pH, along with the buffering system composed of the bicarbonate in your system, okay? All right. So in case of primary respiratory disorders, your kidney, so if you have an issue with your lung, your kidney will compensate. And if you have an issue with your inside with the metabolism, then your lung will compensate it by taking the CO2 out, okay, or leaving the CO2 in. So your lungs and the kidney play in concert in order to balance your blood pH. Okay? That's along with the buffering system that you have in. Now, the compensation, as I said, when your bicarbonate goes up, the pH goes up, that is compensated by increase the CO2. So the CO2 increase, if you suppress the respiration, because you have a high pH, so the body will suppress the respiration to increase the CO2 level. So that will generate more acid, so your pH will come down. That's in case you have metabolic alkalosis. Now, in the metabolic acidosis, for the other hand, the bicarbonate level is low, so the pH is low. In that case, your body will suppress, will stimulate the respiration in order to suppress the CO2 level. So you will respirate very hard to get rid of the CO2, and that will decrease the CO2 level, and then your pH will rise up to compensate. Is that clear? Good. So now the respiratory acidosis, on the other hand, so you have CO2 level goes up, pH is down, so you will compensate it by increasing the bicarbonate for the pH changes. If you have respiratory, your body will try to adjust the bicarbonate, basically by increasing the bicarbonate by getting rid of your proton through your kidneys. Now, the respiratory alkalosis, on the other hand, so which means the CO2 is low, your pH is high, your body will compensate it by trying to decrease the bicarbonate, and that will then help increase your pH in your, that would try to maintain the blood pH in that sense. So if you have a respiratory condition, so your kidney will try to play. If you have metabolic condition, your lung will try to compensate it. And the direction, I know sometimes it's confusing when you look at it, but if you look closely, it makes much more sense to it. Is this clear? Okay. The ionic gap, you'll see this a lot, but I think it's good to touch it. It's a biochemist, but you'll see, clinician will talk about it, and then physiologists talk about it. I think it's important for you to know. So ionic gap is nothing else. It's the sum of the positive ions, sodium and chlorine. You take that sum, and you subtract these out of that, the chlorine and the sum of the chlorine and the bicarbonate. So if you test your blood for these molecules, the blood gases estimated. So you can do this sum, your sodium concentration plus the potassium, and you subtract the chlorine and bicarbonate. That's your ionic gap. Very simple, okay? But sometimes they write it this way, okay? And I think it's good for me to show you both formula in case you see one. But this is the correct way. The reason they subtract the potassium because the potassium sometimes level is very low. So even if you don't utilize that, it won't make big changes, okay? So you will see both formula, but this is the correct one. As far as I'm concerned, biochemistry, this is the correct one. But this is not incorrect either. But it just excluding the potassium because the potassium concentration is relatively low. Okay, it won't make much changes. Okay, so the reason people use this in the clinicians is because he tell you when you have a high ionic gap, say it is an indicator of metabolic acidosis. Okay, especially in the diabetic type 1, the person's not controlling fat mobilization, so the fatty acid breakdown occur. When the fatty acid breakdown occurs, acetyl-CoA get built up, and you have a lot of ketone body production. And those ketone bodies are acid. And because they are acid, they're trying to decrease the pH, the proton concentration, and the pH start going up. Which means at somewhere in the metabolic level, you are producing a lot of acid. So that's indicating the person can suspect, the patient can say, okay, this person has some of these conditions. All these conditions can lead to a decrease in the pH in the blood, okay? And the ionic gap can tell you a lot about that, okay? So now I gave you this to summarize a little bit. So you can put all these things next to each other here, and then in case of metabolic acidosis or up to alkalosis, what is really occurring and what is the compensation? Okay? So it gave you everything that I said earlier, I summarized here, for you to see in one page, okay? All right, so I think that's the end. If you have any questions. No question? Was that total? Oh, you got one here.
Use this. Is it possible for the gap to be low at certain point?
Sure, gaps below, but the much more meaningful one is the when it goes up. Yeah, the gap can be low. Yes. That's it. That's the only question I have. The buffering range. Oh yeah, if you know if the buffering range is, if you know the pKa value of the acid, it is +1 and the -1. So that is the range. And the maximum buffering point is the pH equal to pKa value. So basically, it is a pKa value. That's the maximum buffering point, and the range is -+1. Okay.
For the anion gap, what is considered high for metabolic acidosis?
And as we feel, I can't recall the exact ion gap for physiological condition, but as a biochemist, we'll say if it's higher than, based on this condition, it is a metabolic acid. But I want the clinician to tell you exactly what is the correct ion gap. I know they have the range. For all these molecules, there is a range. And then the optimum range is that outside of that range, so you're higher, and below that, it is low. So that range, I can't recall exactly the range, but the range is, I can give you the value if you're interested. But I'm sure you're going to hear a lot about the ionic gap. But there is a range. Any of those molecules in your blood profile. That's it? In type 1 diabetes, a particular one, the pH goes down if it's not controlled. Because if it's not controlled, insulin is not there, you have a lot of mobilization of fatty acids from fat storage, and those are break down by the liver. And once the liver breaks down the fatty acid to acetyl-CoA, there is what's called the ketone bodies get formed from 3 acetyl-CoA. Those ketone bodies are acids, and then a lot of them are generated in your body, your blood pH drop because they are acid, and they dump a lot of protons in your blood, and then your pH start going down. So that's the metabolic acidosis. So I'm sure you're going to hear a lot about that. Yes. Why proton is not no, this is just the iron, the sodium, potassium, and then they came out with that formula. It's just a convention. Well, it does change, but this is not, it's not, the iron gap is not a dictator of pH. It is an indicator of what's going on at the physiological, but not the pH. All right? Okay, if you have a question, my office is on the Smith Hall, and I'm gonna use, it's written on number 3 now, but it's 433. If you have a question and you have my email address, contact me, call me, come see me. Or if you see him in the hallway, just stop me, okay? And I'll be happy to answer to your question. All right, thank you.